So what we want to do for this example is write each claim as a mathematical sentence where we state the null and alternative hypotheses using proper notation and identify which is our claim. So for our first case, we have that a stats professor states the proportion of his students who pass with a grade of B or higher is 61%. A polling place announces that the mean time it takes to vote is less than 15 minutes in the second case, and in the third, we have that a company advertises that the mean tenure of careers they offer to college students is more than 18 years. So what we're going to be doing here is just bringing in this HO-HA notation and some of these basic equality-inequality symbols to condense those sentences down into this sort of comparative pair. And in our first case, well, for that, we want to see if the grades are in some way the same or different from that value of 61%, where often I hope that more than 60% of my class gets a B, but I don't know. It's kind of hard to say whether or not I really want that. Yeah, it's funky. But anyway, whenever we're talking about our null and alternative, first thing we usually like to do is just write HO and HA so that we know these are going to be in here. And we're going to worry about what the claim is at the very end, so don't write that just yet. And then, okay, we're talking about things in terms of proportions. So our null and alternative, no matter what they are, will be in terms of that value P, where from here, because the statement says that I, or some other statistics professor, claim that the proportion is 61%. The alternative and the null will be in terms of that direct equality-inequality, where the null is the statement with the equals, is that our proportion is equal to 61%, so the alternative is that it is not 61%. And one way you can always think about this is that whichever you're given, the null or the alternative, the other is fundamentally its opposite. So we'll see that as we're getting more comfortable with this, I'll show you a slightly different way you can think about it, where you sort of fill in the blanks in a different order to get to the same kind of idea. But for now, I went through it this way, just because I want you to see all of these pieces exactly as they're presented first. And then from here, if you want to figure out what the claim is, again, that's just a matter of paying careful attention to the verbiage, where it says that the statistics professor states it. They state their claim that the proportion is 61%. Where if you're going to perform a test based on these hypotheses, based on this equal, not equal condition, we call this a two-tailed test. And the reason why we call this a two-tailed test will become a bit more clear when we get into the actual math behind it. Then when we look at a distribution for this kind of test, we'll see that we can have either one tail or the other in terms of what we're looking for. But really, you can think of two-tailed as saying we'll either take bigger or smaller. Either is good enough for us. We just want to see if there's a difference. For our second case, we want to see if that mean is less than 15. So this is where I'm going to talk about maybe that slightly different way you can approach the problem. I want to see in a couple different ways so you can understand that there's not just necessarily the one, it's a matter of what fits best for you. But here, we're given the phrase, the mean is less than 15 minutes. So I'll just write here, and 2, I'm clear on that. Mu is less than 15. I'm not going to worry about whether that's the null or the alternative just yet, but that's where we're starting, and that's what we're claiming. At the very least, you have this information. It's the most important thing in there, so it's probably a good place to start. This is an alternate way you can think about it. This is the way that works for me. So, you got 1, let's write its opposite. And the opposite of is smaller than would be is at least. So the opposite of mu is less than 15 would be that mu is greater than or equal to 15. And then from there we can fill in which is the null and which is the alternative based on which has the equal sign. So here, H null is that mu is greater than or equal to, HA, mu is strictly less than. And I'll say that in some other texts, in particular the one that we used to use for this class a couple of years ago, when we were making this sort of notation, we didn't bother including that at least. We would just say that mu is equal to would be our null in that case. And they were slightly different with their wording, slightly different how they thought about this, but for us, the way we can think about it is that when we're testing if something is smaller, well, bigger also serves the purpose of not being smaller. It's very, very rare that that bigger than case is really meaningful. If it is, we probably did the test wrong, but we include it just because it technically still fits, even though it very rarely gets used. And for this, because when we're looking at our alternative, that's usually what determines the tailed part of the test. But because we're looking for things less than, if we're going to think about that in terms of a distribution, which just float in the back of your head for now, we're looking on the left side. We call this a left-tailed test. And again, I'll explain in a little more detail what exactly a left-tailed test looks like when we start computing them. But from here, let's finish off with our third case, case 3, where here we have that the company says the mean is more than 18. So I'm going to use the same sort of process I did on that last one. I'm going to start by saying mu here is at least 18. Okay, well, that's our claim. And usually we do claim the alternative. We're claiming that something has changed, in a sense. So, our opposite would be that mu is at most 18. And again, we want to figure out what is the null, what is the alternative, just look for the equal sign. This one has an equal sign, so that is our null. And this one doesn't, so it's our so it is our alternative. Words are hard. And hopefully by process of elimination, you can probably tell that if we have 2 there, left here, this is probably right. And for that matter, it is definitely a right-tailed test because we're looking for things bigger than 18. But that's what we would classify this as, and as I said, you'll get a clearer picture of that later on as we spend some more time developing these ideas. But for now, it's just worth understanding that this is what we call two-tailed, left-tailed, and right-tailed, where that determination is made based on what our alternative is, what we're testing the null against. Whether we can take anything in a two-tailed test, smaller things in a left-tailed test, or only bigger things in a right-tailed test. Those are our 3 scenarios, as it were. And again, doesn't have to be perfect yet. I think it'll make more sense as we see more cases. For now, we're just developing the notation. But anyway, from here, what we're going to look at is how we can talk about what these hypotheses are, and then what sort of conclusions we get from them, whether we get things that go with the null or go against the null, and how they can go wrong or, for that matter, go right. But that's what we'll see next.